outcome this week. Last time we discussed about Bayesian reasoning, and that Bayesian reasoning allows us to put prior beliefs into our reasoning and into our reasoning with observations. Now, this is a funny comic which tells you the story that this makes a lot of sense, that you cannot just argue based on sheer observations. So the story goes here that this neutrino detector measures whether the sun has gone nova, so whether it has exploded and, by the way, also burned the Earth. And then this specific detector rolls 2 dice, and if they both come up 6, it lies to us. Otherwise, it tells the truth. And let's try. The detector says that the sun has gone nova, which your belief would say is highly unlikely. But if you just look at the detector and you observe that the detector lies only in 1 of 36 cases, you are most likely to believe that the sun indeed has gone nova, which does not correspond to the fact that the 2 guys here are still around and happily alive. And so a prior belief that the sun goes nova in any near future should be extremely low, and this extremely low prior belief would counter the rather convincing argument that with 35 out of 36, the detector correctly detected the nova experiment. So, but let's continue with Bayesian reasoning and then apply this to machine learning. First, what we need to do is we need to generalize to a larger number of variables, because typically we do not just have 2 random variables, but we have 3 or more random variables. And how do we conceptualize 3 random variables? Well, a random variable has a number of values that it can take on, like a dice can take on 6 values, a coin can take on 2. The weather, if we just distinguish a rain or a sun, would also take on 2, but of course, it really depends on how you model the world. And when you now look at 3 random variables, you have to look at each possible value combination. And each possible value combination would receive a certain probability, which might be very small, like this one here, or rather large. And the joint distribution is defined by having all possible value combinations in all 3 dimensions. If you're now interested in what is the distribution in a particular dimension, let's say we are interested in the distribution over this random variable, which is indexed here with I. What we would have to do is we would have to sum over all the cells of the other 2 dimensions. It's a little bit hard to paint here, and correspondingly sum up all the values of these entries. And then we would find for each value of this I, here, here, and here, the corresponding sum. And one of these 3 values might be higher than the other 2, and we would have a concrete value for that. Now, when we have the possibility to marginalize to 1 or 2 out of 3 random variables, we can then also define the conditional probabilities like this one. A conditional probability distribution of x given y and z is just the joint distribution of all 3 random variables divided by the joint distribution of the conditions. And this gives us a conditional distribution then with 3 random variables conditioned on 2. Of course, we could also condition just on 1 random variable. And we have again effects like that x and y are independent from each other. They don't influence each other if the conditional distribution of x given y and z is the same as the conditional distribution of X given Z. So basically, whether I know something about Y does not change the behavior of X. And again, what we can do for the three-dimensional case, we can define the product rule. This is an important rule to know. What is the joint distribution? It's the conditional distribution based on the probability of this condition. And this probability of this condition, that's what we know from the two-dimensional case, is this conditional distribution times the prior distribution of C. And with all this knowledge, we can now reformulate this conditional distribution in this way. So we have possibilities to arrange these random variables in a myriad of ways, playing around with our different terms. And we can generalize that to n random variables. And this is a little bit tricky with regard to the notation. What is important here to know is that then we call each random variables as some xi's. And when we are interested in the vector of all random variables, we describe it like this, namely the 1:n means that we include every random variable x1, x2, x3 until xn. So the joint distribution is then described by this notation. And when we are interested in a particular random variable, we just marginalize, that means we sum over the atomic entries in our overall joint distribution. Okay, and we can also define conditionals. And the conditional is described by just leaving out in the denominator the variable x1 that we have in the nominator. Of course, which variable we call x1 is entirely up to us. So this, of course, is a generic way of describing such a conditional distribution with n random variables. And just like we did it for the three-dimensional case, we can likewise describe a product rule. This is something that we will need for our classifier, namely that the joint distribution is described by the product of a series of conditional distributions where each xi, for example, x1, is described by the conditions of all the larger indexed random variables. And then, of course, when we describe this conditioning, we can further unfold this, and we will use this actually in our machine learning simplification in a few slides from now. So, and there you'll see it, how this works and how it helps us. Now, with all this background knowledge, we may perhaps go back to this background knowledge when we see its application now in our naive Bayes classifier. What does the naive Bayes classifier do? The naive Bayes classifier looks at the probability that an object that we have not seen before falls into a particular class. And when we return this probability, this can be considered an f hat, which is a soft naive Bayes classifier, because it gives you a probability for any of the available classes. Here, with the lowercase c, we would have picked a particular class and returned the corresponding probability for this class. Now, what we typically do a hard classification, which means we are interested in the class that maximizes this probability. So we go through all the classes that we have and return this argument that produces the highest probability. And this will be just a single class. Now, we could say this is our C hat for our object. Now, how do we do this? And for this, we use the Bayes theorem. Because we don't know this probability. Remember, that the object is unknown. So how would we know which class does it belong to? Well, we use Bayes' theorem, and what goes into Bayes' theorem? First, there goes in the prior probability for any class. So if an event is extremely unlikely, like the sun going supernova, this would be a tiny, tiny, tiny probability, and the probability that our observation somehow falls into this class is very unlikely, super unlikely to occur. So that's one part. Then the next part is our likelihood. We describe how often a category produces a certain object. And the interesting part about this is that this is something we can observe. So we can look at our data. We can look at how often in our data category produces a particular observation. And of course, we need to have a good representation of our category in our data in order to do this. For the supernova, this would be very difficult because we have not seen much in our solar system. We have seen some in other solar systems, of course. And then there is the probability of the object. Now, this is basically impossible for us to assess. However, it's not a big deal for us because what we care about is the highest probability. And the probability for the object in the first place is the same probability for any class. And so we basically can ignore this. It's just a constant in our argmax computation. So the important point now is that we estimate our likelihood from our training data. Now, the way I described it to you, we have considered the non-naive Bayes approach. And what is it about the non-naive Bayes approach? Well, the attributes and the class labels are interdependent random variables. For example, let's assume we want to classify a car as fast or slow, right? And let's say we have something like a random variable for the brand. And one of the different brands may be a Ferrari. And then further ones. And now we could also have a color. Color could be an attribute, and then we would have red and blue and so on. And we would be interested in classifying a car as fast or slow depending on attributes such as brand and color. But now, what if every Ferrari always is red? That means there is a connection between these different values. In this case, maybe even a connection which is very strict, but even a stochastic statistical connection would influence how we classify our car as being fast or slow in our non-naive Bayes classification. So how does this look like? Non-naive. We use our naive Bayes approach. Now, we have not seen this object before, but what we know about this object are its attribute values. So the object here is turned into a vector of attribute values. The car might be turned into red and brown being Ferrari and whatever we might know as attributes about the object that we might not have seen before. Then we apply our Bayes theorem. And this Bayes theorem includes how often see we this category of cars, how often do we see a fast car, for example. We have this normalization here, the probability of the object, which we don't know, but in the end we don't care about because all we care about is the comparison of how, because this is the same for all different classes. And what we now have to do is we have to calculate the probability that our class, slow or fast, brings about a certain configuration of attributes. Now, this term is very complex, right? And so we can break it down by using our elaboration of how probable this is. So what we can do is we can say this term here is turned into seeing these values x1 to xm minus 1 depending on xm times the probability of xm. Now, what we still have to consider is that we had already this condition, and this condition is dragged along here. And of course, this term has to be dragged along here too. So what have we done? We have moved the joint probability, which we don't know, and have simplified it, and we have extracted conditional probability out of that. Now, we have done this once, but of course we have to do this for every attribute, and eventually we end up with this term where we always condition our series of attributes based on the higher indexed attributes. And we have conditions for these higher indexed attributes. Now, what is the problem here? Somehow we had this original complexity, and we were not really able to make it much simpler. And the reason that we were not really able to make it much simpler is that we have a very long condition, and the more we unfold our terms, the longer this condition becomes. So let's look at this again on this slide. So here I've been doing the same as on the previous slide. I looked at just the likelihood. The likelihood is described by our attribute values. And now I have unfolded this step by step into the conditions until we end up in this place. We define the probability of seeing a value for x1 given these conditions, and a probability of seeing a value for x2 given these conditions. And what is the problem now? The problem is that these many conditions means we are only supposed to count in our data this value if we have a particular configuration here. And this particular configuration is a configuration that we will hardly ever observe in our data set, right? So if you just even assume that these m minus 2 many attributes of this term are binary values, then the condition here would be 2 to the power m minus 2, would allow for 2 to the power m minus 2 many configurations. Yeah, if we have an m which is like 12 attributes, that would be already 2 to the power 10, which is 1024 many different configurations. And if we have m equals 22, then this would be already 1,000,000 many different configurations. So when we have so many configurations, this means that even in a very large data set, each configuration can be observed only very few times. And 22 attributes is not yet a large number of attributes, and binary attributes are, of course, the smallest assumption that you could have. You can, of course, have attributes with many values. So very quickly, with a little bit more than a dozen attributes, you take a large data set, and each individual configuration that corresponds to a condition happens very infrequently, and only in such a configuration you will be able to count how often a particular value is observed. This is a huge problem. You can hardly ever observe such value in your dataset. You don't have this problem for this term here, because here in the data set, you only look for your categories like fast or slow. And let's say you have even just a data set with 1,000 different data items, and if fast and slow appears with approximately the same range, you could observe a particular value here, maybe 500 times, or if it's binary, 250 times, once for fast and one for slow. So when you have very few conditions, even in a moderate sized data set, you can observe a particular value sufficiently often and then have a good estimate of what this probability is. Now, where does the complication come from? The complication comes from the fact that the attributes are not independent from each other. So I have many values of an attribute that come in the context or have to be described in the context of other attributes. Now, the idea of the naive Bayes assumption is that we ignore these connections. We make the assumption that our attributes are completely isolated from each other, which we know in reality they don't are. So Ferraris are very often red. In our terms here, this becomes visible by the fact that we throw out all the further conditions that are not related to the class. So we do as if this probability is the same as this probability. So we ignore all the further conditions for the occurrence of our value x1 and set these to equal, which is not true in general, which is why this naive Bayes assumption is an approximation of the true underlying values. Now, with this trick, we can use our Bayes theorem, apply it to our attribute values, and rather than looking at how particular attributes co-occur together, we just multiply each probability how a category leads to an attribute observation. So we look into our data set and count for fast cars, how often does red appear, how often does Ferrari appear, and these would be different xi's, xj's. And this counting, even a moderate sized data set, will give us reasonable probabilities, which we use and multiply. And then for a particular class, we just have to apply this rationale. And as I said, this probability for seeing attributes, regardless of the category, is a probability we don't really know or we don't really care about, because it is the same probability in all our comparisons. So we just discard it and say that this probability, our posterior, is proportional to this term here. And then we compare these proportional terms and pick the one that gives us the best overall value, and then just choose the category, the class, which has given us this best possible value. So now it's very easy for us. We estimate from our training data how often do we see fast cars, red cars in our training data, how often do we see that a fast car is red, that a slow car is red, that fast car has a different color or a slow car has a different color. And same for the brands, and we just describe our probabilities by these observations or relative frequency of observations. Let's play this through with an example of a very tiny example. Here we have some wine. We have a very small data set consisting only of 5 items. The first item has red wine color is an old aged wine and belongs into the class good. And then, for example, in the last line, last row, we have a white wine which is young and which is bad. And now we try to learn a knife-based classifier to classify a new wine, unobserved wine, into this target class of good and bad. So what do? For example, we are interested in what is the probability of a red and young wine to be good. Well, taking into account our knife-based formula, this is, well, proportional, I should say here, to the prior probability of seeing a good wine. What is the prior probability for that? Well, it's 3 out of 5 cases. And the probability of a good wine being red, well, of these 3 good wines, 1 of them is red. And the probability of the good wines being young, well, out of these 3 good ones, only 1 is young. And so if you combine that, we have an estimate for good, which is 1 divided by 15. We do the same thing for bad, and the probability for bad, of course, would be the 2 divided by 5, and we count among these 2 how many of these are red. Well, it's just this one, so this would be 1/2, and how many of the bad ones are young? This is just this one, and so this is also 1/2, and so we end up with this term of 1/10. Now we can compare what is the proportional probability, not the normalized probability, that a red and young wine is good. That's 1 divided by 15, and correspondingly the probability that a red and young wine is bad is 1 divided by 10, and so the latter is a larger number than the former, so we classify the wine as a bad one. And that's how our knife-based classifier works. So we estimate our probabilities simply by counting. We're looking at the frequencies in our data set. And well, we do this by counting the priors, just by looking at all the different rows and seeing how many of the rows fulfill the condition that they have the right category, and we normalize by the number of observations, the number of rows that we have. Here is another example with mushrooms, and this is a little bit more elaborate, but it's basically doing the same thing, and I think it's very instructive for you to look into the numbers and see how the categories work. But the example basically works in the very same way as I demonstrated for the simple wine example. So I will not really go much into the details of that, but I have to go into the details in case we have a problem. And what could this problem be? Well, let's look into this table again. What if we are interested in such classifications, and for some of the categories, like here we have mushrooms with the 2 target categories, edible and poisonous. What if for some of the attributes, like this one here, we never observe that, for example, a particular shape of a cap is poisonous? Then, of course, this means that we have a 0 probability. For example, this one here, what is the probability that a poisonous mushroom is in the habitat wood? So D here stands for wood. So habitat is something we have here, and the woods is something we have here. So, well, if we bring this into our formula, then a new unseen object described by attributes has a probability for a class proportional to the prior probability of the class. So poisonous and edible, there are like about 3 times as many edible ones as poisonous ones. Okay, not a big problem here. But then for each of the different attributes, we multiply with the probability that is resulting from this specific attribute value. Now, as soon as we have here a zero value, a single zero value, the overall product will be zero. This, of course, is problematic. And it's problematic because it means that if somewhere we have missing data, we would never classify a mushroom as being poisonous. Although, let's say 9 out of 10 attributes might point into the direction of this being a poisonous mushroom. So how can we deal with this problem? Well, the method to deal with that is Laplace smoothing. And let's look back into our table. This table has already collected numbers. So this table is not the raw number, but this table here describes our edible and poisonous mushrooms according to the different attributes. So how many of the poisonous and the edible ones have a particular shape like bell or convex or flat or sunken, and we have here already the aggregated numbers. So out of the poisonous mushrooms, 0 are bell-shaped. Out of the poisonous mushrooms, 20 are convex. Out of the edible mushrooms, 29 are bell-shaped. Out of the edible mushrooms, 34 are convex. So for a particular attribute, these are all the mushrooms that we have, and the attribute combinations then are numbers are spread over these different combinations. So these are all, and these are the combination of edible with a particular shape. And the same is true for these are all mushrooms, and the particular combination is spread here. So now the problem lies entirely with entries that are 0. Why are such entries 0? In general, even in large data sets, we will not observe any particular case, just because there may be very many combinations. We have here a tiny data set. It's less likely. We have a small number of attributes only, so we have a good chance of still having sufficiently many observations. But even with a data set of 100 mushrooms, with these observations, the number of observations is not sufficient. Now, how do we deal with the zeros here? Now, the idea of dealing with them is that we introduce pseudocounts. We say that even if we have never observed something, we add the number 1. We say that instead of 0 observations, we have 1 observation. This is a pseudocount because we have not observed it. But then we do not, that would of course mean that 0 or 1 would not make a difference. And therefore, in order to counter that, we introduce a pseudocount to every possible value combination. And that, of course, leads to a new assessment of the situation, a new probability distribution for our conditional distributions here. And this is described by this Laplace smoothing formula, which basically means if we're interested in a particular combination, we do the counting and then add 1. And we do this for all the possible combinations. And now, of course, this means that we have, for a particular value, now a new value of of observations. So, for example, we have for this particular value now 29 plus 9 observations. And this is something which we have to add here in order to do a correct rejudgment of our probabilities. Instead of adding 1, we can also add a smaller number. This is then the generalized additive smoothing or Lidstone smoothing. And we could use, instead of 1, we could use 0.5 or any arbitrary number, as long as that number is different from, is a positive number and is different from 0. Okay, that's what we get here. Now we can reassess our probabilities. So the probability that a mushroom is poisonous and as a gill color pink. So let's see, where is the gill color? Here we have the gill color pink, and instead of 3, we now have the value 4. And we have to consider under the condition poisonous, how many are pink? So we have to add here the 9 plus 7 is 16, plus 1 is 17, plus 4 is 21, plus 5 is 26. So the 26 comes from this new count of attribute values. Likewise, for this conditional distribution and also for the value for a given poisonous, we see the habitat being in the woods. But now here you observe that previously this would have been 0, and now we have a count which is different from 0 and a probability value which is different from 0. And now, of course, for a new object that's described by all these different attributes, we can then correspondingly compute all these conditional distributions. And of course, here we had the prior for a mushroom being poisonous. And then we can compute the probability that this object is poisonous. And we do the same thing for edible, that this mushroom is edible. And then we compare the two numbers and find that poisonous gave us a slightly larger number. What you see already here is we have a small number of attributes, and what you see here is that these numbers here, these probabilities, tend to become very, very small. I mean, they are not even really probabilities because we have not considered the normalization constant, which would further reduce, further lower the number. But anyway, the terms become very small because we multiply these numbers that are all below 1. And of course, if you multiply many of these numbers below 1, the more you multiply, the slower you get to approach 0. So we have very often numbers, probabilities that are very, very close to 0 and sometimes even hardly discernible. Now, with these many multiplications and in many small numbers, we may run into issues of accurate representations. We have, when you use a float, for example, the problem that the number system, the representation on the computer, cannot accurately represent these numbers. And in order to avoid this problem, we do not compute actually the multiplied probabilities. But what we care about is how probable is it that an observation produces a class. And we said that this is proportional to this probability here. Now, the logarithm is a function like this. And this is a strictly monotonous function on the positive line. And the probabilities, of course, are strictly positive. We have made sure that they are not even zero. And that means rather than comparing these multiplied numbers, we take the logarithm, and the logarithm of a product is the logarithm of the individual parts added up. And the addition is a numerically more stable computation than the multiplication of small numbers. Now, be careful, what is not entirely right here is this proportional sign here, because what is preserved here is not really the proportionality, meaning it's the same term multiplied by a certain constant that we don't care about, but all that is preserved here is the ordering. If one probability for one class is higher than the probability for another class, then this ordering is preserved here. So this sign here for proportionality is not entirely correct. Okay, wonderful. So we have dealt with zero probabilities, we have introduced smoothing, and we have also dealt with the problem of numerical stability. Now, naive Bayes is not always applied like this, because sometimes some more problems arise. What are further problems? Well, one problem being that in an application like text, we have very, very, very many attributes. So how are texts typically represented? Quite often by a bag of words model. What is a bag of words? It basically means we have a certain dictionary, like here, containing all the words, this cloud, and then we describe a particular document by the counting how often words appear in a document. Data might appear 7 times, web appears 8 times, and the appears 100 times in one document. And in the next document, abacus appears 7 times, the appears 50 times, and of course, maybe something else appears 0 times. Actually, in most documents, most words don't appear at all. Now, when we have looked at our naive Bayes classifier, we are interested in, does a document belong into a certain category? So categories might be a good or bad document, a document that's spam or not spam. And as we said, this is proportional to the prior for the class times these different conditionals. But what we have to consider is, well, in the simplest case, we don't even care about the numbers, but we care about whether what is the probability for every word that appears or that does not appear. Let me reformulate this, because I think I didn't explain it super well. Each of these documents here are described as a vector. And for each document, let's say if this is D1, we have our words. Let's say words would be a bag, abacus. At some point, there would be data. At some point, there would be is. At some point, there would be web. And for a particular document, we give here specific numbers. And each document is a vector of such numbers. The document 2 would, for example, have the number 0 here for abac, but 7 for abacus, and so on and so forth. So we have attributes which are described by their frequency, sometimes even just by their presence, whether they are present or not present. Now let's look at this simplified representation. It only says it's there or it's not there. The problem is that we have very long vectors here. So these vectors, when we consider all the words that appear in documents that we care about, this may easily be 10 to the 4 or even 10 to the 6 many words, like 10,000 different words. Or if you look at a larger corpus like English Wikipedia, you may easily have more than 1 million different words. So you have a vector that's 1 million long. And in order to classify a document, you have to consider every entry in this document, every entry in this vector, and compute the probability for the different classes. How is this done? You take the probability, for example, for a bag occurring 0 times for a particular class, and abacus appearing 0 times, and abandon appearing 0 times. And now the problem, if you do this multiplication 10 to the power 6 many times, these are many multiplications for classifying even just a single document, and most words don't appear in a document, so most of these multiplications are rather useless. So the idea is then to say that the terms which are not present do not affect the class association. So let's only include those terms that appear in the documents, and let's also involve the term frequencies, not just whether they're there or not. So then what we do here, we reformulate this problem. We will eventually use the Bayes theorem. So we take the likelihood. How likely is it that a class produces a document? This is the same as the probability that a class produces a particular document vector. With the one difference that in this document vector, we only care about those terms that are actually present. And so we can ask, how likely is it that a category produces the first word times the second word times the third word times, and here is the length of the document, for example, the nth word that appears in this document. Now, some words will appear multiple times, and if a word, let's say, the probability of the in a certain category C, and the typically appears more than once in a common English document, then if the appears 100 times, we would say this is this probability appearing 100 times. So we have 100 times multiply this probability. And this is described here by saying for every term like the, how often, what is the term frequency of this term in this document. And so what we then basically do is we multiply over all the terms that appear in the document. For every term, we take this probability and we take to the power how often this term appears in this document. Now, how do we estimate probability that a term appears for a particular category? Well, what we basically look at is just for all the words that appear in a category. We talk here about this category frequency of a particular category. How relative frequently does a particular term appear? And when we have a certain category and we have never observed a particular word in this category, we also don't want to we want to avoid that a particular term has a zero probability, because if then a term appears in a document, everything points that to the fact that, for example, this document is spam, but it never was observed in a spam document. We don't want to make this probability nil. So we also do a Laplace smoothing here, and we add to the probability of a term appearing in a particular category. And of course, we must then normalize, correct for the normalization, and add for many different terms the number in the denominator. Now what we get is a multinomial naive Bayes classifier. Why is it multinomial? Well, it's we have a range of categories, and for all the different categories, we consider the corresponding probabilities. And we pick this category among all categories that we have, where we first look what is the prior probability of this category, where we see how many documents appear in this category relative to the set of our training documents. Then we go through the size of our vocabulary. So how many different words do we have? And we take the collection frequency of our term relative to the category. So what we do for this is typically we merge all documents that appear in this category into one document and then count how often a particular term appears. And we take to the power the term frequency in how often a term appears in this document that is to be classified. And while we do the same kind of trick that I've shown you before, we do not multiply these small probabilities, but rather sum over the logs of these probabilities. And here is a worked out example. This worked out example represents each document by a vector. So implicitly, each position is associated with a particular word. This is an implicit association. Of course, you have to manage it somehow, but with each document vector, you don't store individually where a particular word occurs. You just know by your management that agency always appears in the first position of the vector, and airplane always in the second, and so on. And here we have entries only for those words that really occur in such a document. So it's a sparse representation because most words don't appear in a document. There's basically no document here that has all the different words. Of course, having just like a dozen words as we do here is not realistic. We would usually have in a document maybe a few hundred words if it's a longer document, or at least a few dozen words if it's a shorter one, and the overall size of the vocabulary is, as I said before, maybe 10,000, maybe 1 million, but much larger than can be visualized here. So we have this sparse vector representation for document 1 and document 2 and document 3 until our document 30, which is here the size of our training data set. So we have here 30 training documents. Here we assume we have 3 target categories as indicated in the last row, which are either economics, politics, or tourism. And so this gives us these category priors. All of them occur exactly 10 times. That's, of course, coincidence of the example. And now we want to compute how probable is it that economics produces the term agency. And So here we have an aggregated representation for our different target categories. It's done similarly as for the mushroom data set. And in all the documents that are classified as economics, the term agency appears 4 times. Let's move back. So here in these documents, how often does the term agency appear? This is exactly these 4 times. So that's represented here. And we do this for all the different words. And of course, then we also see how often words appear in each of the categories, or how many different observation of words we have in each of the categories. So agency appears 4 times. We do some Laplace smoothing here. For the Laplace smoothing, we have to consider the number of occurrences of terms in the category economics. And since here we have 13 different words, we have to consider that each of these words got an additional fictional observation. And so this, considering this all overall, brings us to a probability for seeing agency in the category of economics with a relative frequency of 0.06. And we have to do this for all categories and terms. And if now we have a new document, and this new document has the term agency once, island twice, journey twice, and beach 4 times, then we have to compute the posterior for all of these 3 different categories. And for computing the posterior, we take the prior. This was 1/3 for each of the 3 categories, but now we look into economics, and there it was also 1/3. And then we basically do a lookup for these 4 different observations. Agency is observed once, so this is the probability here to the power 1. Island is observed twice, so this is this probability to the power 2. Journey is observed twice, this is this probability to the power 2, and beach is observed 4 times, this is this probability to the power 4. And this gives us a certain term, as that we would usually add the logarithms and not multiply the products. And now we have to do the same for the 2 other categories. And then what we find is that this is, relatively speaking, the largest probability. And therefore we would say that tourism is rather the right kind of classification for this document. And you can do this likewise for another example.